Okay, so welcome to Physics 2020. I'm just going to say a couple things from the syllabus. If you took Physics 2010 with me, a lot of things I say in the next 15 minutes will be old news, so feel free to check out to an extent. Um, and we will just go ahead and get through it. So first, I am Professor Wade. Nice to meet everyone, sort of. I'll actually meet you hopefully in about a week. But my office is Manning 220. It is very close to our physical classroom. So if you're facing the classroom and you turn right and walk down the hallway, you will see my office on the right. Office hours are 1 to 3 every day, although drop-ins are usually fine. I'll let you know if I'm just really busy with something, but they're usually okay, and emails anytime. I try to be kind of creepy fast in my responses if I can, so that you can continue with your work or whatever it is you're doing. So just email me if you have a question, and I'll do my best to answer it as soon as I can. What else? So nothing's changed as far as for anyone's Physics 1. None of this should have changed. For the grade distribution, the main things I want to point out are that pre-lecture assignments and homeworks are the main two assignment groups for at-home stuff. Everything else is in class. And I will assign the first pre-lecture today, but for some reason, they made chapter 18, 19, and 20 of the textbook the most ungodly long chapters you've ever seen in a textbook. So it's going to be a while before anything is due because it's a very long chapter and pre-lecture stuff is due at the end of the chapter for me. Extra credit is similar to last semester. You can get 5 points on your final grade by doing seminars or adaptive practice assignments on Wiley. Quizzes. I have in-class quizzes. They're announced when I can remember. Otherwise, it's just the day after we finish a chapter. If you miss a quiz, then you just email me, ideally before we take the quiz. Like it can be the morning of, but just before class starts to let me know that you're going to miss it. And then I will hold off on going over it so that you can make up the quiz. But please be punctual about making it up because otherwise you're kind of holding the whole class hostage until we can get your quiz made up. So I want to get those kind of made up as quick as possible after they're missed so that we can continue on. Homework, same as usual, still through Wiley. I'll talk very briefly about getting connected to Wiley because I'm sure it's all old news. And I think that is it for what I want to say from the syllabus. So now I'm going to hop over to Canvas. This is what you should be seeing, something like this. I'll go to student view real fast so I can see exactly what you're seeing. If you're ever wondering what's graded, what's not, you can double check on the Canvas page guide. So the things in red are graded, and everything else, it just explains what those other pages are on Canvas. On every module, I'll post the guided notes up at the top when we start a chapter. I'm also going to try to be better this semester about having additional examples for each chapter. So they're not up just yet, but later today, I will have this additional examples page up, and it's got recordings of really just however many examples I feel like getting to for that chapter that are relevant or have the time to get to. And I think that's the main things there. For getting connected to Wiley, you are either in Smart Start or you're not. If you're in Smart Start, then there should never really be an issue with Wiley because it's set up to not even require that code and course materials thing that other textbooks require. I don't know why. If you have opted out of Smart Start, you should still have access to Wiley stuff right now, meaning all the assignments that you're seeing in Canvas, as well as the textbook over in Wiley course resources. Eventually, that will change. It will be sometime after the opt-out date, which is the 26th. I don't think they've shifted that back. After that time, eventually it'll sign you out and say you need to purchase an access code to continue using Wiley Plus. So if you've opted out of Smart Start, that will eventually happen. Just be forewarned so it doesn't surprise you. Can't forget Gabby. So if you were in Physics 2010, you know Gabby. If not, this is my dog Gabby. She's the unofficial mascot of all my courses. And you will see her pop up as extra credit questions on exams. They're not like, what's Gabby's favorite color or something. They're like physics questions, but with Gabby in them. And you will see her face on quizzes. So if you do well on quizzes, you get the good physics Gabby, and on exams, if you do well, you get the even rarer green good physics Gabby. Should be a great physics Gabby, but I don't know why I didn't do that. Before I turn my camera off, because I will have to, um, in order to do the notes, otherwise you'll be looking straight up my nose because the way I set my tablet up. Let me see if I can find her real fast so everyone can see the real life Gabby. There she is. It's okay. Okay. This is why you rush through the syllabus so you have time to see Gabby. Says hello. Okay. All right, I'll set you down. Oh, she wants down. Okay, here you go. So back to the notes. Okay, and I do need to turn off my video now so that you don't get a weird camera angle of me while I'm taking notes. All right, so we are talking about mainly electricity and magnetism in Physics 2. So we need to start by talking about kind of what electricity is, why we would bother. And so I'm just going to list a few examples of where it comes up that you might not realize it comes up. We're used to it in everyday life stuff, in your phone, in games, in your car, in anything we see almost. There's some sort of electronic component to it. But physically, to exist, we need electricity. We need it for chemical reactions. We need it for, there's something called the action potential associated with nerve impulses for your brain, for your heart, for your other muscles to contract. So you need it for muscle contractions. You need it for your heart to beat. You need it to see and to think. And in fact, you even need it to hear. So it is a very prevalent thing in our existence. And so we want to understand it a little bit better. And that's what we aim to do in Physics 2. So we start from the beginning, the things everyone's heard, but maybe have not thought too much about or don't really know what they mean. The first kind of starting point is that when you rub certain things together, sometimes they exert forces on each other. That was the first observation of electricity in human history by the ancient Greeks. For instance, I will take vinyl and wool. I rub them together. When I pull them apart, I may find that they attract. With the magic of recording, I can actually show you that. So I was extra yesterday. I went into U of M and recorded a bunch of demos so I don't have to hunt down random ones on YouTube. So this is the closest I can get to actually doing in-class demos. You'll have to forgive any weird editing or wording or anything because I had to make these pretty fast. All right, so I'm going to let him do the talking because it's me. I have a piece of vinyl. I'm going to rub the wool on the vinyl. And let the vinyl swing to a stop. And now, if I hold the wool up to the side I rubbed the vinyl on, let's see. that the vinyl quickly turns around to swing towards the wool. In other words, it is attracted to it. Okay, it has been demonstrated to you. When you rub vinyl and wool together, they attract each other. These were not the first things that were rubbed together by earlier scientists, but they formed this long list of things that this works with. And so 17th century scientists, who were the first ones to really consider this seriously, the Greeks saw it almost as a party trick. They called these objects electric. And that comes from a Greek word electron. Does anyone know what that word means? You have to remember the Greeks did not know what electrons in atoms were. They had no concept of that.
Is it some sort of attraction descriptor?
Okay, yeah, that's a really good guess. Anyone else?
Does it have to do with like the charge being or like something being negative?
So negative actually is a relatively new descriptor for charge, but it's also a very good guess. That's from the 1800s-ish.
Someone in the chat said partially negative charge.
Okay, so yeah, we're kind of latching on to these properties, which makes a lot of sense to do, and that's why you're never going to get it. It means amber. Where that comes from is that amber is one of the things you could rub and feel this attractive force. In fact, you could rub your hand on it and feel the hairs on your hand be attracted to it. You could also rub it and then hold it up to paper, and the little bits of paper would dance underneath it. And apparently, at some time in history, women who had amber jewelry would, at parties, we're talking like 1600s, would rub that jewelry and hold it up to little frogs to shock them because it was fun to them. So it really has nothing to do with what we think of electricity nowadays, but that is where the word comes from. The next observation we make is that things don't only attract when we rub them together. Sometimes there are things that repel. And so we distinguish these things by this new property of matter that we call charge. It's a fundamental property like mass that things just have, and it's kind of hard to explain in any other way other than it is a property that they have that makes them interact in this way. So we might notice if we expand on that experiment from before, so I take 2 sets of vinyl, 2 sets of wool, rub the vinyl on the wool, and then rub the other piece of vinyl on the other piece of wool. We can build up this table of interactions between the two. So we've already seen that in these cases where you hold the vinyl up to the wool, that they attract. Okay, then I might find that if I hold vinyl up to vinyl, something else happens. If I now take 2 pieces of vinyl, rub the wool on each, let that one swing to a stop while I rub the wool on the other piece. I don't know what was going on with my hands in this one. I could not hold that piece of vinyl to save my life. They slip over each other in a weird way. Anyway, then since these have been charged in the same way, we'll see that they repel each other. Okay, so we're still in middle school science, but we found that if you hold vinyl up to vinyl, they repel. And similarly, if you had held the piece of wool you rubbed on one piece of vinyl to the other piece of wool you rubbed on the other piece of vinyl, they would also repel. So these are our possible interactions of these things. And we notice that like things repel, unlike things attract. And so since we've done the same thing to the 2 pieces of vinyl, we're going to say they have the same type of charge. That's where like charge comes from, that idea. we're going to just arbitrarily, and it is arbitrary, decide to call these negatively charged. And so I'll say I've got some negative charge on this piece of vinyl, negative charge on this piece. Okay, that forces my hand for all these others. And now for the wool, I can't call it negative as well because it does something different from what the other piece of vinyl did. So I'm going to give it a new name for its type of charge. I'll call it positive. And I am being careful about the number of little plus signs and minus signs I'm doing. I'm doing 5 each. Nothing super special about the number 5, just that it's the same number for everything is what's important. Okay. Now, based on whether other things are repelled or attracted to vinyl, I can then term them positive or negative, and I will build up these further 2 camps. Since I see no other type of interaction, no third possibility, I eventually realize there are these 2 types of charge and 2 only. And so we come up with the general rule that like charges repel, unlike charges attract. The closer you bring those charges together, the stronger that attractive or repulsive force between them. We saw that in the videos of if I held the vinyl closer, you'd see the other piece of vinyl swing faster, and same with the wool. If I was holding it a foot away, you may not see anything at all happen. Okay, so already just this basic idea is useful in everyday technology. E-ink is pretty much solely based on this idea. Now it's implemented in a pretty interesting way, but it is really just attraction and repulsion of charge. So these displays have a base layer that can have a voltage put on it at different points, meaning your kind of pixels of your screen. That's covered by these little capsules that are each filled with a bunch of tiny beads. So millions of beads on these screens. And then you've just got your glass display on it. What's inside those capsules is this inky looking liquid, and then the little beads are white. The beads maintain a negative charge. And so, depending on whether the base layer where the pixels are is set to a positive or negative voltage, we'll talk about what voltage is a lot more later, those beads will be attracted or repelled. So if the base layer is set to positive, the beads will be attracted to it. And so they'll come down towards the bottom of the capsule, leaving that dark inky liquid up top, and that forms a dark pixel on the screen. If the beads, or excuse me, if the base layer is set to negative, the beads will be repelled by it. And so they'll go up towards the top of each little capsule and form a bright spot, a light pixel. And that's why you only have these 2 values on e-ink displays. Although color e-ink displays are coming in, I'm guessing they just use color filters, but maybe they do something a little bit more interesting than that. Who knows? So just attraction and repulsion of charge is enough to build something like this if you're careful enough. I read up on this a little bit, and these guys spent a very long time workshopping this idea until they got something that was consistent. Does anyone know where the terms positive and negative came from? Who decided that charge should be broken into the camps of positive and negative?
People in the chat are saying Newton.
Newton? Okay, so that is a really good guess. He, as far as I know, didn't do a lot of study of electricity specifically. He studied light a lot, and that is related to electricity in a way we'll see a good bit later. It was actually a good bit later than Newton. It was Benjamin Franklin. So that's his major contribution, or one of them, to the study of electricity. He actually did quite a bit. But we're going to come to find out that which one he called positive and which one he called negative was a bad choice. He had a 50-50 shot and he got it wrong. We'll see why here in just a minute. Something he didn't know was this atomic nature of matter. And that is, we know things are made up of protons, neutrons, and electrons, and that is where this charge originates from. On a microscopic level, it is these charged particles. So protons, we know have a positive charge, neutrons have no charge, electrons have a negative charge. The masses of these things are also going to be important, so they're worth writing down. The mass of a proton is 1.673 times 10 to the negative 27 kilograms. The mass of a neutron is almost the same, 675, and the mass of an electron, 9.11 times 10 to the negative 31 kilograms. And you're already seeing my flagrant disregard of significant figures here, so we don't worry too much about them in this class. One thing worth mentioning is that the proton and electron have exactly the same charge, but opposite each other, so equal and opposite. The masses are very different, though. The proton mass is about 1,800 times the electron mass. So that's another weird quirk of nature. Another property is that normally materials have equal numbers of protons and electrons. And so you get no net charge. You have an equal number of positive and negative. So in total, they add up to 0 overall effective charge. And when that happens, you have no electrical forces. That's what we normally see in everyday life. If we rub things together, we start to see a transfer of charge. Now, this is another important thing, and this is something that was not known until pretty recently, as far as, I guess, the history of science. So this was, I want to say, early 1900s that the electron was actually detected. It was, it theorized for quite a while, but actually detected not until I believe the early 1900s. But when objects are rubbed together, it's electrons that move between the two things. Protons do not move between them. There are cases, and you can have positively charged ions that move, but that's more special cases of things. So in this class, at least, electrons are the only thing that move from one object to another in charging processes. And so this is where we see Franklin's mistake. To get a net positive charge, what do you have to do to the electrons on something?
Make them go away.
You got to remove them. So to get a positive, you take away. That is already confusing. To get a negative, you add. And so really, his choice had nothing to do with the idea of electrons specifically. He just thought of some things as having positive and some as having negative. It just boils down to when you find out that they're made up of electrons, that forces the electrons to be the negatively charged thing. And that is unfortunate. We're going to see that come up in several different ways throughout the course. So I will say, to his credit, before Benjamin Franklin, it was thought that there were two types of substances moving back and forth. There's a positive substance and a negative substance. And actually, they thought it was like an invisible fluid flowing between substances. What Benjamin Franklin contributed is said, I think it's just one thing moving back and forth. It's just whether you have an excess of it or a absence of it, a deficiency of it. And we realize now that thing is not an invisible fluid, it is electrons. If we add or remove electrons, we change the net charge of an object. So for wool on vinyl, we said that the vinyl is negatively charged and the wool is positively charged. and that makes them attract. So this is our vinyl, this is our wool. Which one lost electrons? Which one gained electrons?
Would it be that the wool lost electrons since it's positive?
Yep, perfect. And the vinyl gained electrons. And now, maybe this is obvious, but the electrons the wool lost are the electrons the vinyl gained. That is a law of conservation of charge. So it's not, as far as we know, anywhere in the universe, in any charging process, you don't just see the electrons lost from something blip out of existence, and you don't see them blip into existence elsewhere. There is a continuous motion of that charge from the wool to the vinyl. Seems obvious, but it is a statement that has to be made. And so we'll write it out in more detail in a minute. Okay, but now let's consider some different materials. So I'll swap out the vinyl for glass. Okay, I'm going to show you a video of this, and I want you to try and answer the question that I ask. So we know what rubbing vinyl and wool together does now. Which way each becomes charged. But now, say I rub glass and wool together. If I hold one up to the other, they attract. What does this say about how wool charges vinyl versus how it charges glass?
Would they repel?
So I'm asking, what is the charge on the glass versus on the wool?
A glass is
Would the glass be negative charge and the wool is positive? So
Okay.
because the glass and the well, I don't know. Go on.
Yeah,
Sorry.
no, finish your thought. Finish that reasoning because I think it'll lead you
Oh,
to the right
I was
spot.
thinking because it's the glass is repelling the vinyl, so that means they are the like charge because they're pushing against each other instead of coming together. So they're
Did
both negative charge, the glass and the vinyl. So
did
that
the
would make
glass repel the vinyl or did it attract it?
Attract.
The glass is attracting the vinyl. So do you want to revise what you think on that charge?
Wouldn't it be the same thing as the one on the left?
What would negative charge do to negative charge?
they would
repels.
repel.
They would repel. So if the glass were negative, it would repel the vinyl. Is that what happened?
No, it
No.
was attracting it. So the
So
wool would be positive, right?
what did I hold up to the vinyl?
Glass is gonna be positive and wool is gonna be negative.
Yeah, the glass is positive because when I held it up to the vinyl, it attracted the vinyl. So they must have opposite charge, unlike charges attract. But through this conservation of charge, that must mean that electrons were removed from the glass and they were added to the wool. Now, I did use the same piece of wool, and so really it would be this previously positively charged wool being partially neutralized. But if I had used a separate piece, we would see the wool become negatively charged because of those electrons being added. But we would still get this attraction between the two. So depending on the materials, one material likes to lose electrons, the other material likes to gain electrons. And it depends where they sit in something called the triboelectric series. So you don't have to know this bit, but if you want to look more into it, it tells you what likes to lose electrons, what likes to gain electrons as far as which materials. let's talk more about those two facts of charge. I'll talk about conservation first. So that's just the idea that charge always comes from somewhere and it always goes somewhere. So if I go back up here, I can say, all right, any electrons added up at the top or electrons removed from the bottom, or on the other side, any electrons removed from the glass were electrons added to the wool. If I consider my system consisting of both things, what can I say about the net charge of that system before and after I rubbed the two things together? So what was the net charge before I rubbed them together?
Neutral.
It was neutral, so the net charge was 0. What about after?
0.
Still
Yeah.
0.
Yeah, because I have an equal amount of negative and positive charge. The individual objects are charged, but the system has 0 net charge. That's another way of saying conservation of charge. So net charge of system remains 0. Now, if I brought in a third object that I didn't consider part of my system, then I would not be conserving charge within my system, but it's because I have this thing that's being taken out of the system. Okay, the other big thing that is now obvious to us, but was not for a very long time because we didn't know of electrons or protons, is that charge is quantized. It's always an integer multiple. Of the electron charge. Because all charge is made up of some excess or deficiency of electrons. And so the total charge you have has to be a multiple of your individual charges. That's all that's saying. We can write it as an equation. If we say Q, which is the letter we use for charge, I really don't know why on that one. I really think it is we just ran out of letters. Because C, what does C get used for? I guess mostly heat related stuff. And the speed of light, I guess that's the biggie. But I don't know why the speed of light is C other than celerity, maybe. Anyway, Q equals NE, where N just represents any positive or negative whole number. And E is what we call the fundamental charge. It is just the charge of an electron or proton because they have the same size, same magnitude of charge. And so all that's saying is any amount of charge I have has to be some multiple of the electron charge. It could be 1 billion electrons worth of charge. It could be 10 million. It cannot be 1.5 electron charges. It can't be pi electron charges. It has to be a whole number. It can be negative a certain number of electrons because that would be a positive charge, right? It just has to be a whole number multiple, whether that number is positive or negative. The unit we use for charge, by the way, is the Coulomb, abbreviated C, named after Charles Coulomb, which we'll get to his law a little bit later. Then we will start distinguishing between types of materials. So you can distinguish not only between which likes to gain or lose electrons, but also how easily those electrons move in and on the material. So charge moving through a material is called conduction. So charge can be conducted. And so We know of several good examples of conductors. Metal is one. So what happens is you set up what you might call a gradient of charge. If you put something negatively charged on one side of a conductor, so this is a conductor, and you put positively charged something on the other side, then the electrons in the conductor can move easily through it. So which way would these electrons in this material move?
To the right side.
Yep, they'll be repelled by the left and attracted towards the right. So conductors are things that, unsurprisingly, readily conduct charge. On an atomic level, the reason for that has to do with energy considerations. It's based on the amount of energy required to pop the electrons out of their individual atoms. So it's mostly the valence electrons, the outermost shell of electrons, that contribute to conduction. And if they're not strongly bonded to their individual nuclei, then it takes very little energy to pop them off and move them through the material. What are some examples of conductors? I said metal, but give me, like, what are the best metal conductors?
Gold.
Gold,
Copper.
copper, silver's one. Does anyone know which of those is the best conductor?
I want to say gold.
You're right. That's why expensive electronics use gold-tipped stuff, because they can claim that it helps improve. Usually it's like audio stuff where they get really snobby about it. In some cases, it is useful to have, but you are more used to seeing copper in things because it's the cheapest of those that is still a pretty good conductor. So it actually goes basically most expensive to cheapest is also best conductor to worst. So gold is better than silver, is better than copper, but also in price. Okay, what are some other conductors? Not metals anymore.
Water.
Water. So as students of chemistry, you may know that ionized versus deionized water has different chemical properties because of the amount of free electrons in it, the amount of really ions of different salts and things. Okay. And what's something that's made up of 70% water?
Humans.
Yeah. Unfortunately, we are pretty good conductors. And one more you may not know is Earth. The ground is a relatively good conductor, and that is a very useful property for it to have. It can serve as a very large source or sink of charge. Insulators are the things that don't conduct charge well. And so those are the ones that really don't like to let go of their valence electrons. They're strongly bonded. What you call the band gap of them is very large. That's the gap between the valence band and what we call the conduction band. That's getting more into quantum related stuff, but that's what's going on under the hood. It needs a lot of energy to separate those electrons. And that energy can come from things like friction, rubbing things together. And that's why most of the things we saw up above, like vinyl and glass and wool, are insulators, because they can really only separate charge through significant inputs of energy like rubbing. So things like rubber, plastic, and glass. I forgot to mention for conductors, sometimes that valence electron or the valence electrons in them that can easily move through the material because they're really not tightly bound to any one nucleus. That's sometimes called the electron sea. You may hear that term sometimes. Okay, but this is important. In either case, the positive charge ain't moving. There are exceptions, plasmas, some usually liquids, whereas ions flowing, but we don't talk too much about those in here. Okay, so we've seen at this point mainly one type of charging, which is friction. You also probably aren't too surprised that you can charge something by just touching it if you've got things that easily transfer charge. So I want to show you a tool that we can use to check if something is charged. And that's something called an electroscope. Okay, so this is called an electroscope. You can see it's a glass jar with a rubber stopper in it. Up top, you've got a metal ball that's connected down through to inside the glass, where you see two little foil leaves. What the electroscope is used for is to see if there is charge on something. So, if I touch it with something that's not charged, like my hand at the moment, nothing happens. But if I, for instance, charge up my PVC with wool, then I will see that it has some charge on it. And I've deposited some on there. Since my PVC is an insulator, it doesn't really like to let go of a lot of that charge. But you can see I've deposited some on there, and so the leaves are now separated. Got a little stopper, got our bulb, got our leaves down here. How does this thing work to tell us that something's charged?
So what I think is that like the bulb is the one that's collecting all the electricity and it
Mhm.
takes it up to the leaves. But since there's nothing that's holding the leaves, like like holding the charges together, it expands out like electricity, as you can see, like we saw in the video.
Yeah, so if I touch something charged, like, so PVC, I skipped ahead of myself a little bit, but PVC polyvinyl chloride is chemically similar to vinyl, so it's going to be our substitute kind of from here on because it's easier to use to tap stuff with to charge it. Um, and so that's going to deposit some electrons on this. They flow easily through this metal bulb, and so they can flow down to the leaves. They actually spread out over the entire surface of this metal, but some flow down to the leaves. And so why do the leaves spread apart?
They're both getting electrons, which is the same charge, so they repel off of each other.
Perfect. So that's all it is. Just a very simple device, can't really be used for quantitative anything, just to see if something is or is not charged. There are versions of electroscopes that can be used to see exactly how much charge, but they're fancier than this one. Okay, so you're going to see this thing used in a few different places, so I just want you to know what it is and how it works. The last thing I want to show you before we call it a day is something that's a little bit different from what we've looked at. I'm just going to ask a question in the video, and I'll leave you to think about it until the next class. So let me pull that one up. I now have a piece of wool, a PVC pipe, which is chemically similar to vinyl. I'm going to rub them together until the PVC is charged up. I've got an aluminum can here. I'm not going to touch the can. I've not done anything to charge it up. I've not rubbed anything on it. But if I hold the PVC near it, you can see that the can is attracted by the PVC pipe. So if I've never charged the can, how is it being attracted by the PVC? Okay, so you have enough information to reason that one out. So try and see if you can. And on Wednesday, we'll discuss more and look at a couple more examples of that phenomenon. Are there any questions before we call it a day today?
No, sir. Have a good day.
All right. Thank you. You too.
So I was wondering,
Mhm.
you said that like how we're conductors of electricity and so is water and earth and all this stuff. So if my house has metal and there's like some random like electric lightning storm or whatever, where would be the safest for me to stand? Would it be like outside on the ground or
It
like
would be
inside a
inside your
restaurant?
house. And we'll talk about why a little bit later. It has something to do with your house acting as what's called a Faraday cage.
Okay.
It's also why if you can't get indoors, getting in your car is your second best bet.
Okay, thank you.
Yep, thank you. That's a good question.